In this video, we're going to walk through a full proof of correctness and running time analysis for the Heapsort algorithm. At its basic level, Heapsort is conceptually very simple. We will put all of the data elements into a heap, and then one at a time, we will remove the minimum element from the heap, and that will give us a sorted array. All of the complexity here lies in the heap data structure that underlies the algorithm and how we create the heap and how we remove the minimum element. As a reminder, a heap is a type of binary tree, meaning that every node has up to 2 children. And specifically, a heap is always a complete binary tree, meaning that all of the levels except for the last are full, and the last is filled from the left. In addition, this complete binary tree has the heap property, which is that for every node in the tree, if it has children, the node's key is no larger than that of its children. So let's draw an example of a heap. So here we have a binary tree where every node has at most 2 children, and all of the levels of the tree are completely filled in, except possibly the last one, and the nodes in the last level are all the way to the left, so this is a complete binary tree. And we have the heap property because for every node, its children have keys that are at least as large. When we talk about the heap conceptually, we will be thinking about this binary tree representation, but in terms of how the data is actually stored, we can use an array to hold our heap. Because all of the levels are full, we can store the data in an array where the positions correspond to the ordering of a level-by-level traversal of the tree. And as we'll see, if we know the index in the array of one node, we can use that to calculate the indices in the array where its children would be stored. And so we'll use this representation when we're thinking about the heap operations, but we will actually implement those operations using indices into the array. Our pseudocode for the Heapsort function makes calls to 2 functions that we haven't defined, so we should also write some pseudocode for Heapify and remove min. Here we have pseudocode for creating a heap and removing the minimum element of a heap. And both of these functions rely on a helper function called bubbleDown that we'll talk about in a moment. The Heapify function works by first creating a copy of the array and then working backwards from the end of the array to the beginning, calling bubbleDown on each index. In terms of our conceptual drawing, working backwards through the array corresponds to starting from the bottom of the tree and working our way up to the top. To remove the minimum element, we first swap the items at the first and last indices, which corresponds to swapping the root of the tree with the last element at the bottom. And then we call bubbleDown on index 1 of the array, meaning that we are bubbling down from the root of the heap. So the idea of this bubbleDown function is that it can take one element in a heap that is out of place and push it down the tree until it finds an appropriate location for that key. So let's look at some pseudocode for bubbleDown. As we said, the goal of the bubble down function is to take one node whose key might be out of place and push it down the tree so that the key ends up in an appropriate spot. So let's think about an example of how this would work if we called bubble down on index 1. If we gave it an index of 1, then we would find that 2 times I is less than the length of the array. So we would go into the loop, and then we would check whether the heap at I has a larger value than the heap at the index of the smallest of I's children. So here the children are 3 and 5, and so smallest child would tell us that index 2 is the smaller of the two, and so we would be comparing this node to this node, and we would find that it is not larger, and so we'll go into our else case and be done. And this makes sense because what we started with was already a valid heap, and so there's nothing for bubble down to fix. So instead, let's consider a heap that has one node out of place. Supposing that our root had a key of 5, then that would also mean that in the array, index 1 has a value of 5. So now when we enter the loop and have a smallest child index of 2 and compare that element to the element at I, the if condition will be true because the element at I is larger, and so we will swap those two values. And then we will update I to the index we just swapped to. So I is now index 2, pointing to this node. Then we'll go back to the top of the loop, find out which of the children is smaller, and that's this one. So we'll get back index 4. And so then we'll compare the values at index 2 and index 4. And since the value at I is larger, we'll again go into the if and swap. And now we update I again to index 4. Then we'll go back to the top of the loop. We'll find the smallest child of index 4, which will be index 8, because index 9 is not present in this array. And we'll compare and go into the else and be done. So the result of our bubbling down is that we swapped the value that was out of place until we got to a location where the key was not larger than either of the children. We have two helper functions here, smallest child and swap, for which we have not yet written pseudocode. We're going to write those out for completeness, but if everybody who was going to be reading our pseudocode and our proofs already understood how those worked, it might be reasonable to skip it. Hopefully the swap function feels obvious, and the smallest child function is fairly straightforward, but it's worth pointing out that because we are one indexing the array, and because we have a complete binary tree, it's very easy to calculate the index of the left and right children based on the index of the parent. We multiply by 2 to get the left child index, and add 1 to that to get the right child index. Then we are returning the left child index if there is only a left child, and otherwise we will return the index of the child with the smaller key. Now that we have a complete specification of the algorithm, what remains is to prove its correctness and analyze its running time. We'll begin by analyzing the running time so that I can then get rid of some of the pseudocode to make space for the correctness proof. To figure out the running time of the Heapsort algorithm, we first need to know the running time of the helper functions that it calls. So let's drill down into those helper functions, and they in turn have these other helper functions, so we really need to start at the bottom with the swap and smallest child helpers. If we think about our swap function, each line here is accessing some data in memory and storing it into some other location in memory. So if we have some constant that describes the amount of time it takes to do this access and store operation, we could call that C1, and we are performing that operation 3 times. In addition, there is some constant amount of time associated with calling and returning from a function, and we'll call that C2. And so, if we were going to write down a function to describe the running time of our swap function, we could write it as 3C1 plus C2. And importantly, this does not depend at all on n, the size of the input. In this case, n would be the size of the array that we were given as input to the heap sort problem. And so with respect to n, the running time of our swap function is constant. The smallest child function also has some lookups and assignments, and it's performing multiplication and addition. And we'll say that C3 is the time to perform a basic arithmetic operation. We also have comparison and branching operations, which we could assign another constant. And we have the time required to call and return from the function. So if we wanted to write out the running time of this function, we would get a sum of several constants, but again, none of these constants depend on the size of the input, and so we get big O of 1 running time. And so, because we know that the running time for these functions is big O of 1, we could just call that some other constant when these functions are called elsewhere in the pseudocode. And so at this point, I will dispense with naming all of these different constants, and instead, I will just write big O of 1 in the cases where we are calling a function that we know takes constant time. And so, moving up to our bubble down function, we perform a constant amount of work for smallest child, and now we have a comparison and branch, an assignment, and a call to a constant time function. So overall, the body of this while loop is adding up some number of constants, and so we will get a total big O of 1 amount of work in the body of this while loop. So to figure out the running time of bubble down, we need to figure out how many times this loop can execute. And here again, we can take advantage of big O notation, since we know we are going to be giving an upper bound on the running time. We don't need to know precisely how many iterations, we just need to know an upper bound on the worst case number of iterations. Each time through this loop, we are updating I to become the index of a child, which was either 2i or 2i plus 1. So the one that will make this execute the most times is if we pick the left child every time. And so the number of times that we could double I and still have 2i be less than or equal to the length is the log base 2 of the length. And that length is the same as the input size to our function, and so we could have a number of iterations of this loop that is log base 2 of n. And so overall, on each iteration, we're doing a constant amount of work times log base 2 of n iterations. And so we have big O of log n total work being performed by the bubble down function. Now that we know that bubble down does big O of log n work, we can think about the running time for remove min and heapify that call bubble down. The lines of remove min do constant, constant, constant amounts of work, and then we call bubble down that does a logarithmic amount of work. And when we add all of those up, in total, our remove min function will have done big O of log n work. Now, considering the Heapify function, we can again think about each line that does work in this function. Making a copy of the array requires scanning through the entire array, and so takes big O of n work. And we know that each call to bubble down takes big O of log n time. But in Heapify, we are calling bubble down on each element of the array, starting from the last index and working our way all the way back to the first index. So if bubble down takes worst case log n time, and we are calling it n times, then an upper bound on the running time of this loop is big O of n times log n. So overall, Heapify is doing big O of n work plus big O of n log n work, which simplifies to big O of n log n. Finally, coming to our Heapify function, we know that creating the heap takes n log n time. Then we have a loop that runs for n iterations, and on each iteration we are calling remove min, which we know takes worst case log n time. So overall, this loop takes no more than big O of n log n time, plus n log n time to run Heapify gives us an overall running time for the algorithm of big O of n log n. Of note, there were a few places in our analysis where we assumed a worst case and got an upper bound, and it's plausible that a more careful analysis could have given us a tighter upper bound on the running time of some parts of this pseudocode. One example to consider is calling bubble down as a part of Heapify, because in Heapify we are starting from the end of the array and working our way back to the beginning. So for the vast majority of our calls to Heapify, we will be operating on elements that are closer to the bottom of the tree than they are to the top. And so it's only when we get all the way to the root of the tree that we might actually have to do log n operations in order to bubble that all the way down. So it's at least plausible that a more careful accounting of the total amount of work being done by these n calls to bubble down might give us a tighter bound than n log n. But I will leave it to you as an exercise to figure out whether we can tighten this bound. Now our goal is to prove that our algorithm produces a correct answer to the problem of sorting an array. As we launch into this proof of correctness, it's worth noting that my proof differs from that in the book because I have chosen to write these algorithms using loops, whereas the book chose to write the pseudocode recursively. The advantage of the recursive approach is that it makes an inductive proof of correctness easier because the structure of the inductive proof corresponds to the structure of the recursive algorithm. But I want to use this as an opportunity to give you a bit of a window into my process for thinking about correctness proofs. And so we're going to try and prove the correctness of this version of the algorithm And along the way, I'm going to lead you down at least one false start that I made in coming up with the proof myself, to think about how we can skeptically evaluate the claims in our own proofs and iteratively improve them. So the key idea underlying the correctness of Heapsort is that bubble down can fix a heap that has just one error. So our first goal is to prove that if we have an almost heap where there's only one node that's out of position, then if we call bubble down on that index, it will fix the heap property so that the whole tree is a heap. And so we can prove this by thinking about a loop invariant for our bubble down function. A loop invariant is some property that is true every time we get to a particular point in the while loop. And specifically, the invariant we want to show here is that every time we get to the top of the loop, the only violation of the heap property, if there is one, occurs at node I. To apply this loop invariant, we first need to show that it is initially true when we begin the loop, and for now we're going to assume that we called bubble down on a heap whose only violation of the heap property occurs at position I. Later, when we think about the calls to bubble down being made by the other functions, we will need to ensure that that is actually the case. If the loop invariant is true at the start of bubble down, our next step is to show that it is maintained by each iteration of the while loop. So let's think about what happens in the body of the loop when I is initially here. Well, we will find the smallest child that could either be y or z, and for the sake of argument, let's suppose that it's y. Then what will happen is we will compare the key at location I to the key at location C. And so if x is less than y, we'll do a swap, otherwise we will break. In the case that x is not less than y, we knew at the beginning of the loop that the only possible violation of the heap property was at position I. If we found that y is less than or equal to z, and we've found that x is not less than y, then we know that there is not actually a violation of the heap property here, because the key at this node is no larger than the keys at its children. So, in that case, when we break and leave the while loop, we actually know that there was no violation of the heap property anywhere. What then about the case where x is larger than y and we go into the if statement? Well, then we will swap the elements at index I and index C in the array, which corresponds to swapping x and y in our diagram. And then we will update I to now be here. And so we want to consider, is the loop invariant still true? Is it now the case that if before the only violation of the heap property happened here, now if there is any violation of the heap property, it can only be here? Well, let's consider y versus z. we know based on smallest child that we chose the smaller of these two as the thing we were going to swap with, and so we know that y is no larger than z. And we also know, because we went into this if statement, that y is smaller than x, and so the heap property holds here. The key at this node is no larger than its children. What about at this location? Well, if the heap property held before everywhere but here, then that means that the heap property held at this node and at all of its descendants, and so none of those nodes changed, and the heap property still holds here. At this location, we are allowed by our loop invariant to have a violation of the heap property. So it could be the case that x is still larger than one of its children. So have we now shown that every iteration of the while loop necessarily maintains our loop invariant? Well, there's one part of the tree that we haven't yet considered. Could there be a violation of the heap property further up? Well, whatever this node was has not changed, and its descendants and its ancestors, if the heap property was true there before, it still is now. So all we have to rule out is the possibility that there is a violation of the heap property specifically at this node that was the parent of our old index I. What do we know about this node? Well, we know that the heap property held here before, and so we know that the key w is no larger than the key x. But because we swapped x and y, we know that y is strictly less than x. And this leaves open the possibility that y is also less than w. So let's see if we can come up with a specific example of a heap where this happens, and see if we can figure out what went wrong in our reasoning about bubble down. Here we have a complete binary tree where the only violation of the heap property happens here. 9 is larger than either of its children, but everywhere else the heap property is satisfied. If we were to execute the body of the while loop in bubble down, we would swap the 1 and the 9, but then we would have a violation of the heap property here because 2 is larger than 1. So this problem could happen. If we were to call bubble down on this heap, giving it this index, then we would end up with not a heap, because bubble down would perform this swap and then finish, and we would be left with a tree that still has a heap property violation. So what went wrong here? Well, it could be that there's something wrong with our bubble down, or it could be something wrong with how we're reasoning about the operation of bubble down. And so we should think about, could this circumstance ever arrive when we're calling bubble down in our heapify or findmin functions? And I claim that no, in fact, this could never happen. And there are a couple of different ways that we could argue that. Both of them involve thinking a little bit differently about how we are using bubble down. We could either think about only cases where we call bubble down on the root of a heap, or we could think a little bit differently about our heap property. Specifically, we could make a stronger claim about the heap property that will make it easier to carry out this proof. If we're thinking about a data structure that fully has the heap property, then it would be completely equivalent to write the heap property referring to the children or referring to all of the descendants. But these have a different implication when we're talking about violations of the property. Specifically, this tree has multiple violations of the descendant version of the heap property because node 2 has a descendant that is smaller, and so there are multiple nodes where their key is larger than the key of some descendant. And so if we think about the heap property in terms of none of the descendants having a larger key, that rules out this possibility. And if we know that the heap property was not violated at position W, then we know that none of W's descendants have a larger key, and so when we swap y up, we now know that y is in fact less than or equal to W. So if we state our loop invariant in terms of the descendant version of the heap property, then if it was true at the beginning of the loop, it will still be true when we get back to the top of the loop next time, because the only possible violation would be at the new index I. And so now we need to think about what happens when the loop terminates. Well, there are a couple of ways the loop can terminate, one of which we already considered. In the else case, we know that there is no violation of the heap property because the only place where there could have been a violation was at I, and there wasn't, in fact, a violation there. So what if we, instead of breaking the while loop, get to the end of the while loop based on the loop condition? Well, if 2i is greater than the length of the array, then that means that we have reached some node in the heap that has no children. If 2i is exactly equal to length, then that's the case where the node has one child. Here we have index 3 and index 6, where index 7 is out of bounds. So if we reach a place where there are no children, and the only possible violation of the heap property is at that index, well then we know that a node with no children has no descendants, and so in fact the heap property cannot be violated there, and so whether we exit the loop based on the else case or based on the loop condition, we know that upon exiting the loop, there can be no violation of the heap property anywhere in the heap. And if there's nowhere in the tree that the heap property is violated, then we know that H is now a heap, and so bubble down has taken us from an almost heap with at most one violation to an actual heap. Now that we know bubble down is correct, we can think about the correctness of heapify and remove min. If we think about a call to heapify on an array that is not yet a heap, like the example we just saw, we will loop through the indices of that array in reverse order. So we will first call heapify on the last element of the array. And if we call heapify here, then we can think about just the subtree rooted at that node. And if we think about this subtree, it meets our definition of almost a heap from bubble down. It has at most one violation of the heap property. In fact, it trivially has no violations of the heap property. Likewise, as we iterate back through the other nodes, all of the nodes in the back half of the array are childless, and therefore bubble down will immediately terminate, giving us a valid size 1 heap. If we then come to internal nodes of the binary tree, since we have already called bubble down on every index that is later in the list, then we know that the tree that is rooted here is itself a heap, and so the only possible violation of the heap property in the tree that starts here would be at this specific node. And that means that when we call bubble down on this index, we know that we are calling bubble down on an almost heap where the only possible violation is here. Likewise, when we get to this location, we will call bubble down on an almost heap, and this call to bubble down will make sure that this is actually a heap. Specifically, it will do that by swapping the 1 and the 9. And so by the time we get to here, we know the tree that has its root here has at most one violation of the heap property, because we know that this is a heap and this is a heap, and so the only possible violation is here. So we can think of our calls to bubble down as each operating on a subtree, and for each of those calls, we know that the previous calls have set us up so that the only violation could happen at the root, and since we're calling bubble down on the root, we know that bubble down will fix it. And so what we've done here is argue inductively that the precondition for bubble down's loop invariant will always be met by the previous calls to bubble down. We also need to show that remove min correctly gives us the minimum element and results in a tree that is still a heap. Well, if the thing that was given to remove min was in fact a heap, then the first index of the array must contain the smallest element, otherwise the heap property would be violated. And so we know that when we take the element from the first index of the array and eventually return it, we are giving the minimum element. And then we are performing a swap, and that swap can create at most one violation of the heap property. We swap the first element with the last, and then we remove the last element of the array. And since we knew that the heap property was satisfied at all of these locations, removing some descendant isn't going to violate the heap property. So the only place that the heap property might be violated is at the root, where we swapped in a different key. But we then call bubble down and give it index 1, and so we know that bubble down will fix a heap with only that one violation, and so the result after bubble down is again a heap. And so the result after a call to remove min is that we get back the minimum element, and we have a heap with that minimum element removed. So then, when we call Heapsort, we create a heap, and then n times we will get the minimum element remaining in the heap, and we each time put that in the ith index of the array. So when we have completed Heapsort, we will have put the elements into the indices of the array in ascending order, and we have proven the correctness of our Heapsort algorithm.